Welcome to Lecture 6.4, Complex Fourier Series. So to summarize what this lecture is all about, recall that from Euler's equation, we can write a complex exponential in terms of sines and cosines, and we can go back and forth. So it's reasonable to assume that instead of writing Fourier series in terms of sine waves and cosine waves, we could write them in terms of complex exponentials. And in some sense, this is a more natural thing to do. Okay, so let's begin with a review as to how we derived the original Fourier series. So we had this set of functions, sines and cosine waves, and we had to slightly normalize the constant functions for technical reasons that don't matter. This set is a basis for the 2-pi periodic functions, meaning any 2-pi periodic function like a square wave or a sawtooth wave, etc., can be written as a unique linear combination of these things. And moreover, we could do that. We have formulas quite easily once we realize that with this inner product, 1 over pi, negative pi to pi, f of x, g of x dx, with this inner product, this basis became orthonormal, meaning these functions have magnitude 1 and they are mutually perpendicular, mutually orthogonal. Because remember, when we define an inner product like this, that gives us a notion of geometry. Okay, so here's where we are now. An alternative basis for this set of 2-pi periodic functions is this, a set of all complex exponentials. And this thing really is e to the 0 ix. And this basis is orthonormal with respect to this inner product. Now this is slightly different. So we have a 2 pi on the bottom instead of a pi, but we also have this bar here, which means complex conjugate. So remember what that is if this is z equals a plus bi, then z bar equals a minus bi. So this is just a reflection across the axis. So that's what complex conjugate is. So moreover, let me remind you that if this is a unit circle, if we have a point on the unit circle, let's say this is e to the I times theta, that means this is theta. So the complex conjugate of that is going to be this point down here, which is e to the, or what is that? So this angle is going to be negative theta. So e to the I theta bar equals e to the negative I theta. That's a fundamental fact that will be useful. So when I say that this basis is orthonormal with respect to this inner product, what that means is, that means that if you actually compute this, you take f and g. Actually, let's not do that. Let's actually compute complex exponentials. Let's compute e to the do I want to say I n x with e to the I m x. This is, by definition, 1 over 2 pi, negative pi to pi, e to the I n x, e to the I m x bar, which is 1 over 2 pi times this integral, e to the I n x, e to the minus I m x dx. This integral is 1 over 2 pi. Let's do this. Let's simplify this now. I'm going to write this as e to the I times n minus m x dx. This integral is easy to compute. This is 1 over 2 pi I times n minus m times e to the I n minus m x from negative pi to pi. Let's recall also that e to the I times, what is e to the I times pi? That is the number on the unit circle that is right here, right? So that's negative 1. That's the complex number that's right here. It's pi radians from 1. So e to the I times k times pi for any, actually let's say n instead of, like I'll be using n more, e to the I n pi for any n. So e to the 0 pi is right here. E to the I pi is there, that's 1, negative 1. E to the 2 pi I is there. E to the 3 pi I is there. E to the 4 pi I is there. So this thing is just negative 1 to the n. This is going to be super, super useful. Remember that thing throughout this lecture and beyond. Okay, so what do we have here? This is an integer. This is like k, right? So this thing here is, well, I'll let you check this work. It's not hard to check, but so if these things are different, so if this integral is correct, this is complex exponential, here I am assuming that n and m are different. Otherwise, the integral of this thing, I'm integrating the function 1, not a complex exponential. So given that, in this case, when n and m are different, this thing here is, this number I don't care about, times e to the, this is an integer. So e to the some integer times pi minus e to the negative that integer times pi. These integers have the same parity. And so that is going to be 0 if n equals m, if n is not equal to m. And it's not hard to check that this integral here, it's not hard to check that this thing is equal to 1 if n and m are equal. So this is 0 if n and m are not equal, and it's 1 if n and m are equal. So I skipped over some of the little math details. It's all elementary. If you want to check that, I encourage you to. But the point is, it's not hard to check that this basis is orthonormal with respect to its inner product, because this thing here either is 0 or 1, depending on whether n and m are the same. Okay, so to summarize, because that basis is orthonormal with respect to the inner product, if we have a 2 pi periodic function, then it can be written as an infinite sum of those complex exponentials. So this thing here, I know I'm starting at negative infinity, going up to infinity. Maybe you don't like this doubly infinite sum, so you can always write it like this. You can always just pick off the constant term, and then you can add from 1 to infinity in pairs this n term and the minus n term. And as before, the constant term, c0, is just the projection of f of x onto my e to the 0 function, and cn is the projection of f of x onto e to the inx, which by definition is the integral, is this integral right here, where we have e to the minus inx. It's because this is the complex conjugate of that. So we get these formulas right away for free because of that orthogonality property. Okay, so I will do an example of the Fourier series shortly, but first of all, I want to show you a neat trick of how you can go from the real series to the complex series. So the complex series, recall, is n equals negative infinity. So it's adding up all of these, and sometimes that's just easier to write as c0 plus n equals 1 to infinity of cn e to the inx and c to the minus n e to the minus inx. Okay, so that's the complex Fourier series. And basically, what this is going to come down to is the fact that cosine of something, say cosine of nx, is e to the inx plus e to the minus inx over 2. And sine of nx equals e to the inx minus e to the minus inx over 2I. So this is basically going to help us go from Fourier series with real functions to a complex Fourier series. Okay, so let's do this. So I'm going to write out f of x equals a0 over 2 plus n equals 1 to infinity. I'm going to start with my real Fourier series. So here's my real Fourier series. Now the constant term here, a naught over 2, what's the constant term up here? That's when n equals 0. So that's just c naught. So this constant term, I can write this as c naught, because again, I want to write f of x like this, and so the constant terms better be the same. So now I have a cosine, and I have a sine, and what I'm going to do is I'm going to replace those things with complex valued exponentials. So this is n equals 1 to infinity of a n e to the I n x plus e to the minus I n x over 2. And then next one's going to be plus bn times e to the I n x minus e to the minus I n x over 2I. Okay? I haven't done anything. I've just written these using exponentials. And now I want to combine terms, but I have a 2 here and I have a 2I here. So let's multiply the top and the bottom of this by I. So let's multiply this by I and that by I. So now let's simplify that. So this is going to be c naught plus the infinite sum of an times e to the I n x over 2 plus e to the negative I n x over 2 plus bn. And let's be careful here. So this I in the bottom is going to turn into a negative 1, right? And so this, let's see, so this thing here is just equal to negative 1. So I'm going to swap the order of this. So on the top, this is going to be I times e to the negative I n x minus, I should say I times e to the positive I n x over 2. See what I did? I moved the negative sign up top. And so now, so I meant to switch this into two fractions like I did here, but you can handle this being a sum of two fractions. Okay, so now we have c naught plus an infinite sum of, of something times e to the I n x plus something times e to the negative I n x. And notice this is Cn, and this is C negative n. I mean, that's just the definition of Cn. It's the coefficient of e to the I n x. So what goes here? Well, we have this, and we have that thing here. So in other words, we have so we have an. So there's this term, an over 2. So we have an over 2. And then we have this term here. This is bni over 2. No, this term here, bn negative I over 2. So minus ibn over 2. So that goes there. And then what goes here, it's the negative INX coefficient. So here's one. This is an times, put a parentheses here. Let's put parentheses here. An times an over 2 times this. So that's going to be an over 2. And then we have right here ibn over 2. So plus ibn over 2. This is the coefficient. This is C negative n, and this is exactly what we got up here. And notice that this is true for n equals 0 as well. If you make n equals 0, this is also going to hold. Okay, so let's do the other direction. Let's suppose that we have a complex valued Fourier series, something like this, and I want to write this thing in terms of a real valued Fourier series. So I want to write this as a naught over 2. Now we know that a naught over 2 is the constant term c naught, but what we don't know is the rest of it. N equals 1 to infinity. Let's write an cosine of nx plus bn sine of nx, we would like to figure out what the an's and the bn's are, and I claim here is a formula for that. Okay, so to see why this is, I claim that this all boils down to Euler's formula. You remember that? So Euler's formula is e to the I nx. Actually, let me move that down a little bit. I'm going to run out of room on the top. E to the I nx equals cosine of nx plus I sine of nx. And also, e to the negative I nx is going to be, let me use blue for this, just to make it different. E to the negative I nx is going to be cosine of nx minus I sine of nx. Because remember, the negative signs, they get absorbed in the cosines and they pull out of the sines. Okay, so let's do the same thing we did before. Let's write a f of x equals, let's write it as c naught plus, I think this is going to be a little bit easier to go between the two, this form, cn e to the I n x plus c to the minus n e to the negative I n x. Okay, and now what we're going to do is I'm going to replace this thing with this up here, and I'm going to replace this one with this down here. So this is going to be a naught over 2. Try that again. A naught over 2 plus the infinite sum of Cn times cosine of nx plus I sine of nx plus c to the minus n of cosine of nx minus I sine of nx. So let's do what we did before once more. Let's write this out, and then this thing here involves sines and cosines. So this is going to be something times cosine of nx plus something else times sine of nx. And of course, this thing here is by definition an, and this thing here is by definition bn. So what goes here? Cosines. We have a cn and a c negative n here. So we have a cn plus c negative n. That's how many cosines we have up here. And how many sines do we have? We have cni plus minus I times c negative n. So that's I times cn minus c negative n. And that is exactly what we claimed up here. So we just derived how to go from the real Fourier, from the complex Fourier series to the real Fourier series. Okay, so for the first example, let's take the square wave that we've seen before and used before. So this is, of course, the square wave. This guy, where this is pi, this is 1, and this is negative pi. And so let's compute the complex Fourier series. So C naught, by definition, is the integral from negative pi to pi of f of x dx. This is the area under the curve from negative pi to pi, and that's clearly 0. Alternatively, we could have said that this is the constant term, this is the average value of the function, which is going to be 0 as well. Okay, so Cn is 1 over 2 pi, negative pi to pi, f of x e to the negative I nx dx. This is the definition. So let's compute this. So this is 1 over 2 pi from the integral from negative pi to 0 of the function negative 1 e to the negative I nx plus 1 over 2 pi times 0 to pi of the function positive 1 times e to the negative I nx. So unfortunately, we don't have any shortcuts like Fourier. Like you can't use symmetry arguments here like we could with sines and cosines. But I think these things are a little bit easier to integrate overall, so this is a good thing. So this first term, this is 1 over, let's get my pen back, 1 over 2 pi times, let's be careful here. Now it's e to the negative I n x, that's the easy part. Then I have to divide through by the constant, which is negative I n. So I had negative 1 over negative I n. Okay? And then I have to do this from negative pi to 0. And next, I have 1 over 2 pi. This is going to be that term, 1 over 2 pi times, e to the negative I n x over negative I n. As before, and do this from 0 to pi. Let's simplify this. This first term is going to be, so this minus negative cancels. This first term is 1 over 2 pi I n e to the negative I n x from negative pi to 0. And the second term is I should say it's minus 1 over 2 pi I n e to the negative I n x. I don't need that there, from 0 to pi. Now remember, the super useful thing I told you last time was e to the I n x equals e to the negative I n x does not matter. This is negative 1 to the n. All that matters is whether n is even or odd, and n and negative n are going to have the same parity. And recall why that was, that's because in the unit circle, e to the I n x, if n is even, that's e to the 0 pi I, e to the 2 pi I, etc. We're here. If it's odd, then we're over here. So we're either at an even number of pi radians or an odd number of pi times pi radians. Okay, so this thing here, and also this, same thing works for 0. If although, I guess here we don't need that. Okay, so here we have 1 over 2 pi I n times e to the 0, which is 1 minus e to the negative, plug in negative pi, negative 1 to the n, minus 1 over 2 pi I n times e to the, plugging in pi into here is going to get me negative 1 to the n. Plugging in 0 into here is going to get me 1, so that's going to be minus 1. So if I add these things up, there's a negative sign here, but this is negative of that. So these things are additive. So this becomes 1 over pi I times n times 1 minus negative 1 to the n. And this thing here is, if n is even, this is 0. And if n is odd, we get 2 over pi I times n if n is odd. So now one thing I should mention is that this formula works, this is my Cn, and this works for positive or negative C. I don't need to recompute C negative n. I just need to do this for C naught, and then Cn, and then this thing works for all n, positive or negative. Okay, so let's let's see what what was I going to say about this? Yeah, let's compute the real Fourier series of this, just because we can. So let's use our formula. Do you remember what that was? So the real formula was an was Cn plus C minus n, and Bn equals I times Cn minus C to the minus n. And this also works for n equals 0 as well. So notice A naught is C0 plus C negative 0, which is, so let me write that up here. So A naught is C0 plus C negative 0, which is the same thing, which is 2 C naught. So indeed, the constant term A naught over 2 is equal to C naught. So let's plug these things back into here. I forgot my end parentheses here. Okay, so what's going to happen? So, okay, so let's do it like this. So Cn is 1 over pi I n times 1 minus negative 1 to the n. That's also, so this is also the formula for C negative n. So C negative n is 1 over pi I negative n, let me put the negative sign up there, times 1 minus negative 1 to the negative n, which is the same parity as n. So these things are opposite in sign. So if I add them up, so an equals cn plus c negative n, that equals 0. Because the only difference is that it was this n being negative n. And again, changing this negative 1 to the n to the negative n does not make a difference. Because negative 1 to the n is negative 1 to the negative n always. So next, bn, this is I times cn plus c negative n. So, multiplying by I, there's an I on the bottom, that gets rid of that, right? So now these things are, I made a mistake here, that should be negative, minus ci to the minus n. Let me, trying to think if I should start this, I'll put that negative sign back in red. So let's subtract these two things. And so this minus this, since these are negatives of each other, that's the same thing as taking 2 of this. So this thing here, so I'm going to take 2 of this and I multiply by I, which gets rid of that I. So that is just going to be 2 over pi n times 1 minus negative 1 to the n. And if you may remember, that looks familiar. That is exactly what we got when we computed the Fourier series of this. It was probably the first example that we did a couple lectures ago when we first learned about Fourier series. Okay, so here's our last example. Compute the complex Fourier series of this function. Let me just sketch it. So this is negative pi, and this is pi. Then it's going to look like this. And I chose to make this a half open interval, how I defined it, but it doesn't really matter because at the end of the day, we don't have any control as to what the value is going to be at these discontinuities. Okay, so let's do this. So C naught is the average value, and this one we're not going to be able to do by inspection, so let's just compute it. It's 1 over 2 pi, negative pi to pi, e to the x times e to the minus, I'm sorry, not e to the x, that's right, it's e to the x times e to the 0, so times 1. So that's 1 over 2 pi times e to the x times, or not times, evaluated at these endpoints. So that's 1 over 2 pi times e to the pi minus e to the negative pi. And so that actually is the absolute value of this function. It's not clear, but just from inspection, but it's not hard mathematically. Next, let's compute Cn. So Cn is 1 over 2 pi times integral negative pi to pi e to the x. Here's what I meant. Here's what I wrote the first time, e to the negative I n x dx. There we go. So now, notice that this is not going to be that hard to compute because I can combine these exponentials. E to the 1 minus I x, n times x. And so now I can just do laws of exponents, 1 over 2 pi. I have to divide by this exponent, 1 minus I times n times e to the same thing, 1 minus I n times x. Evaluated from negative pi to pi. Okay, so what do I want to do here? Let's plug this in. This is 1 over 2 pi times 1 over 1 minus I n times e to the Now I got to be careful here. Well, let's do a few steps. Let's plug this in first. 1 minus I n times pi minus e to the negative 1 minus I n times pi. Okay, so this is let's try to simplify this. Notice that this term here, I'm gonna write this up here just to so e to the 1 minus I n times pi equals e to the pi times e to the negative I n pi. And recall that we know that this is negative 1 to the n. So this is e to the pi times, not times e, times negative 1 to the n. And similarly, this next term is going to be, let's check that out as well, e to the 1 minus I n, e to the negative 1 minus I n times pi. That's going to be, just making sure I'm doing this one right. That's e to the negative pi times e to the positive I n pi. And so that's going to be e to the negative pi times negative 1 to the n. Okay, so given that, let's write this, or let's factor out the negative 1 to the n. So this is going to be negative 1 to the n over 2 pi 1 minus I n, and in the parentheses we have e to the pi minus e to the minus pi. Does that look right? Yeah. Okay, so this is our Cn. So this is Cn. Let me box this. So we can leave our answer like this if we want to, but it's always nice to write it as into its real and imaginary parts. We have an I in the bottom here, so I'm going to write this. So I'm going to show you something. I'm going to take 1 over 1 minus I n, and I'm going to write that like a plus bi. So I'm going to multiply top and bottom, you've probably seen this before, top and bottom by 1 plus I, and this is called the complex conjugate. Of course you know that. So if I multiply by the complex conjugate, now the bottom is the difference of squares, so I have 1 squared plus I squared, or 1 squared minus I squared n squared, and I squared is, so minus I squared is minus negative 1, which is plus, so the bottom we get 1 plus n squared, and the top we get 1 plus I n. Okay? So now I can write this a little bit better. I can write this as a little cleaner. I can write this as Cn equals, let's see, negative 1 to the n times e to the pi minus e to the minus pi over 2 pi times 1 plus n squared, and now times 1 plus I n. We do this because now it's clear what the real part and the imaginary part are. Again, this is fine, but I like this a little bit better because now we have the real part is this, and the imaginary part is this, times I n. And one reason why this is helpful is because now let's suppose we want to derive the real Fourier coefficients. Now, one way to find the real Fourier series of this function is to actually compute the a n, b n integrals, and you can tell that there's going to be both an a n and a b n in here because this function is not even nor odd, and there's going to be an a naught, so that's going to involve computing 3 different integrals.
And these integrals are not fun. They would be e to the x times sine nx and e to the x times cosine of nx, and that is not a fun integral. You may remember that's one of the examples of the things where you have to integrate by parts twice, and then you have to move one thing to the side of the equation, and it's a nasty integral. But this integral was not bad. This is just an exponential. And so we're going to use this exponential integral, and then we're just going to use our shortcut formula. So an is cn plus c the minus n. So let's look at that here. So this term here, everything I'm circling, this is the same for n or for minus n, right? The only thing that's different when I plug in minus n is that this thing becomes negative. So that's the complex conjugate. So cn plus c minus n, what that does is that, so the real parts of these things are the same. They're just this thing. And then the imaginary parts, again, are one of them's plus in, the other one's minus in. So those are going to cancel out. So this is going to give me negative 1 to the n times e to the pi minus e to the minus pi over, now there's not going to be a 2 anymore because I'm doubling up the real part, 1 plus n squared. And that's it. So that's my an, because again the complex parts cancel out. And bn, compute that, so bn, recall, is I times cn minus c to the minus n. So what's going to happen then? So now if we subtract cn and c minus n, that is going to cancel out the real parts, and the imaginary parts are going to double up. So cn minus c to the minus n is going to give me it's going to give me this times in twice, but we have to be careful because multiplying by I, that's going to make this I times that I is going to be negative 1. So in other words, this is going to be, let's see, negative 1 to the n times e to the pi minus e the negative pi. Right, now we have, we also have this n here, so that's going to be, I'll put that here, n, and then on the bottom, we're going to have, not going to have a 2 anymore, but we're going to have a pi, we're going to have a 1 plus n squared, and then I have to factor the fact that we have, so this I is there, and we multiply that by this I, so that makes negative 1. So I can either stick a negative sign in front of here, I've run out of room, so instead I'm going to put an n plus 1 right here. So these are the real coefficients. This is an, and this is bn, and I think you will agree that this is much more pleasant, this whole process, of than doing the integrals of e to the x times sine nx or e to the x times cosine nx.